here we're using a stepped-up transformer to connect our standard power around 111 volts to a hydrogen gas discharge tube, which is at 309 kilovolts or 3090 volts. We know the tube dissipates 69.1 watts of power, so what are the RMS currents in the primary windings? All right. Well, there are a couple of ways to go at this. I mean, we've got our standard transformer equation that relates a secondary and primary windings and power, and this is also IP over IS, the currents. Right, the currents equal this same ratio. So we could easily say, well, we know that this is Vs over Vp, right? And so the only thing we don't know, we know the two V's, we know power for one. Well, if I just multiply through with Vp, let's do this, IP Vp, right? All I did was multiply both sides of IP Vp and IS Vs. This is just power in the primary equals power in the secondary, right? So the power, the transformer is not consuming any power at all. It's just transferring power from one side to the other side. And so we know the power has to be the same. And we're asked what is the RMS current in the primary windings. Well, we know the power being dissipated in the primary windings, so we know we have 69 point, we know PP, and we know that equals IP Vp, and we know Vp. So IP is just PP over Vp. A lot of P's in there, right? So the current in the primary windings is just the power that's being consumed divided by the voltage in the primary windings, right? And this is the easiest way to get to that. Just work through the algebra first to get to what is or how should I think about this. So basically we get to very easily the power being consumed on both sides of a transformer is the same. We're delivering power from one side to the other side. There's no loss in the transformer in these simple equations. You can build a model for a lossy transformer, but there's no loss in the transformer for these simple equations. And that's it for this last problem.